Now, let's go over a sample problem using queue. The problem statement is that we want to implement the queue using only two stacks. The queue should support the functions of a normal queue, including push, pop, peek, and empty. This is an interesting problem because queue and stacks have different ordering properties. Queue has FIFO, or first in, first out property, whereas stack has LIFO, which is last in, first out property. So despite these two different ordering properties, we're supposed to somehow make it work and implement queue out of using two stacks. And we'll take a look at how we can accomplish this. Here is a proposed strategy for this problem. Once again, stack is LIFO, or last in, first out, while queue is FIFO, which is first in, first out. This means that stack needs to reverse the order to match the order of the queue. However, one stack by itself cannot match the order of the queue. However, with two stacks, we can use one stack to help reverse the order and another one to store them in the same order as the queue. And we'll take a look at how this can be done. In this diagram, we have two stacks, stack 1 and stack 2. In addition, we already have value A that is already stored in stack 1. Now we want to push value B onto this set of two stacks, but have these two stacks mimic the ordering property of queue. And now let's take a look at how we can move the items around to achieve that property. For step 1, we pop value A out of stack 1 and push it into stack 2. For step 2, once we have relocated the value A from stack 1 to stack 2, we finally push value B into stack 1. For step 3, we pop value A out of stack 2 and push it back into stack 1. At this point, we have both values A and B back in the stack 1, and it's kept in the same order as the queue. As we now see, by moving things across two stacks, we can actually achieve the same ordering property as the queue. Now, let's look at the code implementation of queue using two stacks. For initialization, we initialize with two stacks. One of them is called stack 1, and the other one called stack 2. For push method, before we actually push the value onto one of the stacks, what we want to do is we want to actually pop all the values out of one stack to the other stack. And this is what we're doing here with the first two lines within the push method. Here we're saying that while stack 1 is not empty, we want to pop element out of stack 1 and push it onto stack 2. And once stack 1 is finally empty, then we push that element X onto stack 1. Lastly, we then want to move the values back from stack 2 onto stack 1. So once again, we use a while loop and we do while stack 2 is not empty. We want to pop elements out of stack 2 and push those elements back into stack 1. For pop method, the implementation is straightforward. What we do is that we check if stack 1 is empty or not. If it's not empty, then it's safe to pop the element out of stack 1. So then we'll proceed to do so. Otherwise, if stack 1 is empty, then we cannot pop anything out of it. So then we just return null. For peek method, remember that this method is supposed to only return the first element without actually removing that element. So what we do here is first, once again, we check if stack 1 is empty or not. If it's empty, then we can just proceed to return null. However, if it's not empty, then we can proceed with the operation and return the last element from stack. Note that we want to return the last element from stack because in this case, the last element from the stack should represent the first item in the stack. Lastly, we have our empty method. For this method, we just want to return true if the stack 1 is empty. Lastly, let's analyze the time complexity of this custom queue data structure that was built using two stacks. First, the push or enqueue operation has runtime of OON or linear runtime. This is because the existing elements are being pushed and popped twice, and the current one element being pushed is only pushed once. This gives for n plus 1 operation where n is the queue size. And because time complexity is an amortized analysis, this rounds up to O of n. Otherwise, all other operations, including pop or dequeue, peek, and empty, all have O1 or constant runtime. This wraps up our lesson on queue. If you would like to get more practice, here is the list of recommended LeetCode problems that you can look into.